See, okay, so we're live. Welcome everyone. There's one viewer right now, which I imagine is James, watching the chat. So welcome James in the chat, and welcome James on the stream. I'd like to
Thank you.
say thanks once again for coming out to the stream to sort of brighten up the conversation at a huge depth of physics knowledge, etc.
Always a pleasure to be on the show.
Yeah. So, what'd you just out of curiosity, what'd you think about the video today, or that came out yesterday, I guess?
Yeah, I really appreciate this video because I think that Anderson localization represents maybe a sort of interesting way to explore the interface between dynamics and equilibrium physics.
Yep.
In many body systems, and it was one of these topics that I didn't really know about before I got to graduate school, and yet it's so simple. It's not an extremely, in some ways, the result is very kind of pleasing and maybe even a bit intuitive.
Yeah.
And yet, it facilitates this great connection between these questions about eigenstate thermalization that I know many people, including yourself, are interested in, and questions about late time dynamics and so on. So yeah, I think, and transport measurements and these types of things. So yeah, I think it was a cool video, cool topic to cover.
Yeah, I definitely wanted to sort of get it out there because when you go through undergrad, or the way I was exposed to these things, I found Anderson localization to be very surprising because you get exposed to thermodynamics and you get exposed to stat mech, and then right after those two things, I was exposed to eigenstate thermalization, right? And for me, like, that was the world, right? Like that's it. That's all there is. And then when I came to McMaster, Eric gave this as a recommendation to me, and then it was just like, whoa, like I can throw lots and lots of electrons into this model, and take the limit as the number goes to infinity, thermodynamic limit, and I am not going to get statistical mechanics, which I found personally surprising. Did you sort of have an intuition that physical situations like this could be possible before you specifically heard about localization? Or
I think insofar as I had any intuition about Anderson localization, so maybe the confusing answer to that question would be that when I first learned about Anderson localization, I thought, yeah, of course, that sort of makes sense, right? You have disorder in your system, and if you study a sort of first-year condensed matter course, or if you read the opening chapters of Cattell or Ashcroft and Merman, or any of these sort of standard intro condensed matter textbooks, you learn that the standard way to treat electrons in a metal is to use block wave functions to basically say, okay, well, the electron wave function has to have a discrete translation invariance that matches the discrete translation invariance of the crystal that the electron is sitting in, maybe a copper crystal.
Yep.
And because I'm specifying the block wave functions in terms of k, in terms of a momentum, then Heisenberg uncertainty principle tells me that I have no knowledge of where the electron is actually sitting. The electrons are very delocalized, in other words, throughout the lattice. Now, the block wave functions are, in this sense, one might argue that the block wave functions, much like the plane wave solution, the plane wave expansion, the plane wave functions are not in and of themselves physical from this point of view, because you are sort of defining a specific value for the momentum, but they can be used it doesn't matter. I mean, they're physically relevant in that you can expand physically relevant calculations in block wave functions or in plane wave functions in the case of a continuous electron gas. So when you add disorder to the system, one of the first ways that you might think about that is that in a given instantiation of the lattice, you're breaking the translation invariance, and so you're not allowing the electrons to have this spatially delocalized form anymore. And so that was sort of intuitive to me. What I think is interesting about talking about this, though, with folks like yourself who do thermalization type questions, is that I'd never really thought about the emergence of stat mech from quantum mechanics before. I'd never really thought carefully about what has to happen in a quantum pure state for the local subsystems of that pure state to look like as if they are thermal. And what you realize is that basically what has to happen is that those local subsystems must be very much entangled with all of the other local subsystems you could have chosen. And that's the only way for a wave function, which is a pure state globally, to, on a local sublattice, manifest thermodynamics, statistical mechanics, a sort of Gibbs state or a thermal equilibrium state. And so from that perspective, Anderson localization is kind of surprising, because we tend to imagine that, as you were alluding to in the thermodynamic limit, StatMech just comes out, and lo and behold, in this very simple and experimentally realizable case, it doesn't. And so, yeah, a very maybe counterintuitive result from that perspective, but that wasn't a perspective I had when I first learned about Anderson localization. So it seemed kind of natural to me that this would happen. But maybe, the thing with intuition, right, is that intuition only you always want to be a little bit skeptical of your own intuition. Even when your intuition is right, you want to be skeptical of it. You
Absolutely.
might have your intuition might get you the right answer for the wrong reason, right? So that's something that one wants to be aware of.
Absolutely, and I think talking to you, because I mean we study adjacent questions, and a lot of times we're interested in the same sort of models. But I find it very interesting that a lot of times, maybe I'll find something very surprising, and you'll be like, well, that actually kind of makes sense, right? And then, for example, or you'll find something very surprising, and I'll be like, actually, like that,
right.
that vibes with me pretty well. It's like, the background that you have, we're all specialists at the end of the day. Some people have more general knowledge than others.
Definitely.
But your intuition is really derived from your experiences, and then I guess that's sort of why I like this question. Is this thing intuitive to you? Did you expect this to happen? Because I think it's perfectly valid for something that's unintuitive to me to be completely intuitive, and sort of, I don't want to say trivial. I don't like the word trivial. I don't think anything about this is trivial.
Sure, certainly.
But yeah. So I find that very interesting. That yeah.
Yeah, I agree. I think that intuition is really a function of background knowledge more than anything else, and it's a function of the ways in which you were thinking about these problems to begin with. And so, intuition is definitely not something that is even amongst specialists of, I don't know how one could even make this comparison, but you could say sort of comparable competence in their respective fields. Even amongst specialists of that nature, like you say, something might be very intuitive to one that's sort of surprising to another.
Yep.
Yeah, that's definitely true.
So, you know me quite well, so you basically know that the transition from sort of an ergodic or an eigenstate thermalization or extended, whatever you want to call it, phase, that we sort of regularly, we just assume we have that when we're doing regular StatMech, right?
Mm-hmm.
And then transitioning to a thing that's localized, which, maybe there's a mobility edge, which we could get into, or maybe it's just basically you increase some disorder parameter, and then you go from everything is ETH to everything is not ETH. So this is my favorite transition. It's a transition that happens to the properties of basically all eigenvectors, or if there's a mobility edge, a lot of eigenvectors until you get to a certain point.
Mm-hmm.
Then you get all of them. So coming from in sort of a metal to insulator transition in some sense, coming from your background, a more perhaps you might have access to more phase transitions that would be interesting. What's your favorite phase transition?
Well, my favorite phase transitions, first of all, the thing is that when you study this kind of thing, I just find all of the phases of matter that we've discovered, all of the sort of phases of matter that are really governed by quantum mechanics, to be just totally amazing. I mean,
That's a fair statement. Yeah.
Superconducting phases are amazing. There are out of equilibrium phases, sort of dynamical phases. So you, for example, can have materials, semiconductors, where when you apply a magnetic field through the material, they exhibit what's called the Hall effect, a quantum version of the Hall effect. We can maybe talk about what that is if that would be interesting. But the upshot is that if you have a conductor and you have a current running, say, along the x-axis, and then you apply a magnetic field perpendicular to that, you actually get a current that begins to go transverse to that. and that's coming from the Lorentz force acting on the charge carriers. That's the sort of classical Hall effect. It was discovered in 1878.
Oh, that's interesting.
And then what people discovered was that in semiconductors, you can have a quantum version of this effect where the charge transport in the transverse direction is quantized. So it comes in steps, integer steps of the electron charge. And then in the, I think in the 1970s or 1980s, von Klitzing discovered that you can have a fractional version of this effect. So you can have a quantum Hall effect, but where the charge transport isn't in integer units of the Coulomb charge, but is in fractions of the Coulomb charge. In other words, it looks like as if the electron has broken into pieces.
Okay, that's really
inside
interesting.
of this material. It's fascinating. And
That's
so
fascinating.
people then began, the first person to sort of correctly understand this was, or maybe the first person to propose a wave function that described this behavior was Robert Laughlin, the so-called Laughlin ansatz, we now call it. And it was later discovered that this physics is related in some deep way to the topology of the state of the sort of space of quantum states. And it's now just one example of many states of matter, which certainly exist theoretically, and some of them have been found in materials, and some of them are still being sought after in materials, real materials.
Yeah.
But phases of matter that are characterized by the sort of fundamental topology of this space of quantum states. And these phases of matter exhibit all kinds of remarkable properties. So the fractional charges is just one property. We call these anionic excitations. So in three-dimensional space, people who do physics will know you have bosons, you have fermions. And bosons are particles where if I take two bosons and I interchange their position, the wave function looks identical. And fermions are particles where if I interchange their position, the wave function picks up a minus sign in front.
Yep.
And that's all there is. In three-dimensional space, that's the only kind of particle you can have. Those are the only two types of particle you can have. But in two-dimensional space, you can have these so-called anionic particles where interchanging the two particles, winding two anionic excitations around one another, might result in the wave function coming back to itself, but with a phase out front, a phase that isn't just plus or minus one, but maybe could be some complex phase.
Yep.
Or perhaps you wind the two particles around one another and the wave function comes out to be some entangled mess of other states. And these anionic excitations fundamentally arise because of the topological nature of the ground state. Topology is a property that is sort of a global property. If I have a mug, for example, and I imagine the hole where the handle of the mug is sitting, the topology of that, we would say that that's a surface of genus 1. So the genus is basically the number of punctures in your surface. And no matter how I sort of mold or shape or deform my mug, that hole where the handle is still sitting there. So for example, I could take the mug and I could deform it into the shape of a donut, where the hole in the center of the donut was the hole in the handle. Yeah. And from a topological point of view, those are the exact same type of surface. And so topology, in other words, is robust to these sort of perturbations. You can sort of stretch and deform and perturb your system, and a topological property of the system will remain invariant through all of those deformations. Mm-hmm. And so in these quantum phases that are topological, you can take external magnetic fields, all kinds of noise, you can take disorder, and no matter what you do, to within some reasonable limit, to within there's sort of an energy gap that is kind of protecting this topological order. And so whatever you do to the system within the bounds of that energy gap will protect this topological structure.
I see, okay.
And so this is a really appealing basis for quantum computing. Alexei Kitaev, I don't know if Alexei Kitaev was the first person to realize that, but I think he's one of the sort of visionaries who began to come up with ways of writing down models that exhibit this kind of topological invariance, which have excitations that you can do quantum computing on. Okay. And because of the fundamental robustness of the topology, the qubits, which would be your anionic excitations, are going to be robust to environmental sources of decoherence that plague other attempts at instantiating quantum computation.
This phase transition sounds a lot more practical and very powerful than a localization transition. This is ground state physics, right?
This is topology is always so topological phases are defined in the ground state. So they're they're actually defined. So in particular, there's a sort of degeneracy in the ground state, a sort of size of the degenerate subspace.
Yeah.
And it is the size of that subspace that is protected to perturbation. So no matter, ordinarily, so if you imagine a hydrogen atom, and you imagine an orbital with an electron sitting in it. Yep. Well, if the electron is spin up or spin down, it doesn't matter. The energy is going to be the same. But if I apply a magnetic field along the z-axis, then the spin-up electron and the spin-down electron will differ in energy. In other words, the perturbation from the magnetic field lifts the degeneracy of that state. And that's a general pattern in physics. When you have a degenerate ground state, usually that degeneracy is coming from some symmetry, and if you break the symmetry, the degeneracy is lifted. Well, in a topological ground state, the degeneracy is much more robust than that. So I can have a topological ground state, and I can add things to the system which naively I would expect to lift the degeneracy.
I see.
But because of this topological robustness, that degeneracy stays intact. And what that guarantees is that your ground state is in a sort of huge, messy superposition of states. It's an extremely entangled state of matter. And because it's an entangled state, it's allowed to encode these complex amniotic excitations that have all of these strange behaviors when you wind them around each other. You can kind of imagine that the ground state is so entangled that if I take these two particles and wind them around each other, the ground state is going to encode that information and respond to it in an extremely non-trivial way. And yeah, it's amazing. For me, my great interest in physics is entanglement, in the quantum entanglement of many body phases of matter. And so the topological states of matter are absolutely the kind of holy grail of that kind of physics for me. And so I'm extremely fascinated by those and by the efforts to realize them. Not, personally, my interest is not so much in the practical, although I think it is amazing that these phases could offer a path forward for quantum computation. I mean, that is extremely cool. But I think just in and of themselves, they're extraordinary.
How's it going, Sebastian? Nice to see you. Nice to see you in the chat. Entanglement is indeed extremely cool.
Absolutely.
One of the things that I don't say in the video is that these localized eigenstates. In the ETH video, I mentioned that, you get these volume laws for entanglement entropy. And I guess I'd be interested to hear about these topological states, whether or not they're volume laws or area laws, or it sort of depends.
Yeah.
But these localized states, they obey area laws. If you cut your system into two subsystems, A and B, their entanglement in between the two subsystems will scale like sort of the surface area, the contact area, between those two systems, which is another one of the reasons why you just sort of can't build up enough entanglement in these systems to sort of get something that looks like StatMech.
So in the case of topological,
see you, Sebastian. Thanks for stopping by.
Goodbye, Sebastian. So in topological phases of matter, the picture is very interesting. So these are ground states, and they are ground states that are gapped. And so there's a proof that exists, a theorem.
By Hastings, yeah.
By Hastings, that's right, by Hastings, that proves that in a one-dimensional system with a gap, the ground state's entanglement entropy will scale like a constant, like the boundary between the subsystem and the complement of the subsystem, which in a one-dimensional system is just fixed. It doesn't change, and so it goes like a constant. I think in two dimensions, as far as I'm aware, there is no completely general proof, but the general wisdom is that if you have a gapped ground state, then you will have an area law scaling. And so topological phases are gapped and do indeed exhibit an area law scaling, but with an important caveat. So what Kitaev and John Preskill were able to show, that by sort of strategically partitioning up your system into 4 different subsystems, and by taking a sort of strategic combination of the entanglement entropy on these 4 subsystems, you can construct a quantity which is completely independent of the shape and size of those subsystems, provided that the subsystems are bigger than the correlation length of the system. And what they were able to demonstrate is that this quantity that you can construct actually appears in the scaling of the subsystem entropy.
Okay.
So if I take if I take a region and the boundary of that region is L, of length L, and I scale that region up, the topological or the entanglement entropy on that subsystem will scale like L, like the boundary, but with an additional negative constant contribution. So the expression would look something like, some number which is dependent on the details of the model times the length, minus this number, which in the Kitaev-Preskill paper they call gamma, which we call the topological entanglement entropy.
And sorry, that subtracts off of the...
That subtracts off. And that's really crucial, right? Because if you think about it, the entanglement entropy on a subsystem must be non-negative. It can be zero or it can be positive. And the fact that this subleading contribution is negative means that the entanglement entropy must always have some non-zero positive value in order to guarantee that the subsystem entropy is at least zero.
Yeah.
And this is a sort of residual entanglement, an entanglement that is coming from this massive superposition in the degenerate subspace, the sort of entanglement that is coming from this topologically invariant structure. Yeah. Hence the topological entanglement entropy. And so, yeah, you can show that this thing is independent of the sort of details, as long as the region you're looking at is simply connected, as long as the region you're looking at has, that's actually a bit complicated. So the topology of the region you choose can affect this in ways that are a bit non-trivial. But if you choose a sort of simply connected subsystem, then the subleading, we say in sort of the jargon, is that the subleading contribution is constant and negative, and that's this topological entanglement entropy. So you have area loss scaling, but with this additional term that is coming from the fixed amount of entanglement in your system.
Okay, well, ground state physics is incredibly rich, it seems.
Definitely, yeah. I think that it's a bit tricky because in these systems, the topological entanglement entropy is not something that you can measure trivially in an experiment. Indeed, actually, entanglement entropy is something that we use extensively in the theory community to talk about phases of matter.
I hear there's a measure of entanglement, or an entanglement witness, that someone here is an expert on, that can be used in experiments, or can be observed in experiments.
Yeah, that's right. So there's yeah. So thank you for teeing me up actually to talk a bit about my research here. So as it turns out, there are many different ways of looking at quantum information theory. So in classical information, we have this concept of the Shannon information, or which basically in the physics business, what we call entropy is a sort of special case of the Shannon information. And one way of describing the Shannon information is that it's a sort of measure of how unpredictable a probability distribution is. So if I give you a distribution and it's really hard for you to guess what the next value of that distribution is going to be, then the Shannon entropy of that distribution is high. Whereas if I give you a process that is totally deterministic, the Shannon entropy is zero. And so a pure state wave function, even though it has randomness to it, even though quantum mechanically there is randomness to a pure state, the generalization of the Shannon information for a whole pure state is zero, because the pure state technically contains all the details about the system. It contains all the information you could ever want to know about it. But if I look at a subsystem, right, this is where the entanglement entropy kind of comes from. If I look at a subsystem, then the fact that subsystem is entangled with the part of the system that I'm not looking at means that it becomes somewhat unpredictable to me, because I'm not looking at the entire system as a whole. The whole is sort of more than the sum of its parts. Because I'm not looking at the entire system as a whole, I'm just looking at this subsystem. The results of measurements are going to be unpredictable in a way that is sort of classical. It's sort of like the Shannon entropy. And so that's what the entanglement entropy is really a sort of measure of. Well, there's another quantity in classical information theory, which is basically the second derivative of the Shannon information. It's a quantity called the Fisher information. And it basically measures, if I give you a probability distribution And say I give you a coin, and the coin has a particular weighting to it. So maybe it's heads or tails, but the probability of heads isn't 50-50. The probability of heads is 60%. And I imagine that the probability of heads is a sort of parameter I can tune.
Yep.
I can ask the question, how easy is it for me to distinguish a coin that is weighted 60% heads from a coin that is weighted 61% heads? And the speed with which my ability to distinguish those two coins changes as a function of the weighting is the Fisher information. So it turns out that in the quantum world, quantum states are made more distinguishable from one another by the presence of entanglement. So if a quantum state is extremely entangled with respect to a certain measurement that I'm making, it's much easier to distinguish. If you imagine maybe I have a quantum state, and maybe that quantum state depends on some underlying parameter, theta. If that state is extremely entangled, then there's a sense in which it's easier for me to distinguish theta from theta plus a small little change in theta.
Yep.
And it's been demonstrated that this quantity relates directly to what's called genuine multipartite entanglement. So in other words, when we talk about the sort of standard von Neumann entropy story, we imagine I give you a wave function and I say to you, factor the wave function. So factor the wave function into a wave function on system A times a wave function on the complement of A.
Yep.
And if you can do that, then A and the complement of A are not entangled. And if you can't do that, then there is some entanglement measured by the entanglement entropy. But what if I want to do this problem, what if I give you 50 subsystems or 100 subsystems? What if I'm talking about a system that has millions of particles and I want to know how entangled each individual particle is with each other particle?
I see.
Sort of genuine multipartite entanglement.
Yep.
The Fisher information measures that and can be detected through response functions. And so an area that I'm extremely interested in at the moment is looking at different ways that you can use the Fisher information, which is experimentally accessible directly, to probe the entanglement structure of these topologically non-trivial ground states.
Yep.
Yeah, and so I think this is a very interesting and much work has been done. I should say that much work has been done on this. There's a great paper. I think it's actually called Multipartite Entanglement of Topological Phases, and I wish I could recall the names of the authors. Maybe someone watching will be able to pull it up. Worth a read, and they sort of do a very nice theoretical study on how the Fisher information for various. There are some technical details that one has to think about when looking at the Fisher information, but they basically study how the Fisher information responds to different topologically non-trivial phases. And so inspired by that work, I've also done some work, published some work looking at a model, again by Alexei Kitaev, a model that has a topologically non-trivial ground state in one of its two phases, and how the Fisher information behaves at the interface between these two phases, and whether we can say anything about topological order. And so, yeah, that's a major area of interest for me, certainly.
Yeah, it's a really cool, it's definitely a really cool topic. I hear the phrase sort of entanglement witness thrown around. Would you mind expanding and explaining on about what that means?
Sure. So entanglement is not like other, there in the sort of standard story of quantum mechanics, there are things like the magnetization of the system, or the I don't know, the Green's function of the system, the likelihood of an electron to go from point A to point B in a system, things like this.
Yep.
And these type, or the number operator, how many electrons are sitting in this well, something like that. So these types of observables all have associated to them an operator, a Hermitian operator in the sort of technical jargon. And so they're sort of understood as operators that act on the wave function, and they extract observable information, and you can go do an experiment and measure them. But there are other properties of quantum systems that don't have a Hermitian operator associated to them. So for example, the relative phase between two wave functions doesn't have a Hermitian operator, or the amount of time that has elapsed. If I give you a quantum system and it's evolving according to some dynamics, I might ask you, make measurements of this system and tell me how long it's been since such and such a moment earlier on. There's no Hermitian operator associated with that. Entanglement is like that. Entanglement as a quantity is something it's well defined. We understand exactly what it is in terms of this notion of can you factor the wave function, this notion of producibility,
Yep.
as it's sometimes called. But there's no Hermitian operator associated with it. So an entanglement witness is an operator that you can construct, which isn't measuring the entanglement directly, but it's sort of telling you at least how much entanglement you might have in the system, or whether or not entanglement is present by some amount.
So it's like a lower bound somehow.
Yeah, I think here it gets quite technical. I don't want to.
Okay, that's
I
fine.
don't work on entanglement witnesses, so I don't want to say anything too definitive here. There are some good reviews that people can refer to, but I think that basically the idea is that you're sort of constructing an observable quantity that is as the name suggests, a witness for entanglement. So if this quantity has values above a certain threshold, when you measure it, okay, well then I know that there maybe is like at least this much entanglement in the system, or at least this much, or at least this type of entanglement, this much of this type of entanglement in the system. Something like that is sort of what the entanglement witness is doing. And so it's trying to build a bridge to something that is observable that you can use to test whether entanglement is there. Incidentally, there are all kinds of these things. There are all kinds of things which, depending on who you talk to, might not be described as entanglement witnesses per se. There may be, you might call them algebraic witnesses of entanglement. So, for example, you can have something called the negativity. So, in the negativity, you take the partial transpose, you take the density matrix, and instead of tracing out one of the subsystems, you take the transpose of that subsystem and then the trace.
Yeah.
And if that quantity turns out to be negative, then I believe the statement, and I'm sure someone will correct me if I'm wrong, I believe the statement is that if that quantity turns out to be negative, then you have entanglement present. And so this type of thing, these types of sort of algebraic tricks that you can do on the density matrix to try to see whether entanglement is present. The problem with so many of these, though, and this isn't, entanglement witnesses are kind of trying to solve this problem, I think. The problem is that with something like negativity, you need to know the density matrix to do that. So from a theoretical point of view, if I can write down the density matrix that corresponds to a system, I can use something like the negativity to determine whether or not entanglement is present. Yeah. But for an experimentalist, especially an experimentalist working in a condensed matter context, that's not going to be a useful way of learning about entanglement by and large. You don't know as an experimentalist the exact density matrix of the state that you're measuring.
Yeah, it's easy to forget things like that. Being a theoretical physicist who's sort of boxed off like a level abstraction away from people who are talking about real materials theoretically, and then below them you actually have experimentalists. So working on real materials, it's sometimes I forget that. I guess I don't forget, it just never crosses my mind that a lot of the things that I'm doing and a lot of things that I'm like talking about bipartite entanglement entropy and stuff like that, like that's not something, I mean, it's of course interesting, it's interesting physically, but it's not something accessible physically to an experimentalist per se. You need things that they can actually look for to discover. Definitely. Yeah, to sort of discover the things that you're interested in seeing.
Yeah, absolutely. I mean, there's actually some recent neutron scattering work where they measured the Fisher information in a model that has a sort of effectively one-dimensional spin chain.
Oh yeah.
And a one-dimensional spin one-half chain. And so this is now a place where the theory of entanglement is really starting to make hard contact with the work that experimentalists at neutron scattered.
Weren't you cited in an experimental paper? I guess that's sort of the dream, right? Like you do theory, and then people who work on real things feel the need to insert you into the conversation.
My work was cited in the context of sort of corroborating so the work that I had done in this context was on the spin 1 Heisenberg chain. This experimental result was on a system with a spin 1/2 Heisenberg chain. Okay. The general wisdom is that the lower the spin moment is for the individual degrees of freedom, the more quantum behavior will be. Yes. The larger the spin moment is, the less quantum things become. And so my work was cited in the context of sort of I don't know if I would say corroborating, but sort of emphasizing this fact that experimentally they do indeed find that the entanglement that they witnessed was higher than what I predicted you would witness for a spin 1 chain. And so we were
Nice.
given a nod in that respect, which was yeah, definitely much appreciated. It's always wonderful. If I wish I remembered the name of the yeah, this is another one. I'm not so sharp at the moment, but I wish I remembered the name of the paper. The experimentalists, they were at the big neutron facility in Tennessee there.
I see.
Yeah,
It's hard to sort of keep track of all of these. I mean you wanna give credit where credit is due, but I think it's
absolutely.
I think it's fair. I forget. I'm really bad.
Oak Ridge.
Oak Ridge?
Oak Ridge National Lab is the
nice.
the experiment was done.
I am incredibly bad. I know like 5 names. No, that's not true. I'm very bad at remembering names unless it's a paper I've looked very hard at, or it's a paper that I'm currently looking at.
It is difficult. It is difficult to keep up with the pace of research right now, especially when you're doing condensed matter physics, because at the end of the day, the pace of research in condensed matter physics is just extraordinary. It's by far the sort of biggest field of physics out there. Maybe I want to be a bit careful in saying that. I've been told something like on the order of 60% of publications in physics are coming out of what is broadly called condensed matter.
Yeah.
So,
regardless, it's a gigantic field with lots of. If you're anywhere in the field, there are going to be tons of adjacent fields with interesting results that you want to keep your eye on, right?
Absolutely, yeah, absolutely. I think that's true. And this language of entanglement, I think, is really something that unites a lot of the active areas of research that are going on right now in condensed matter physics.
Yep.
I mean, the most interesting phases in the ground state have to do with phases that are exhibiting a high degree of entanglement, and a lot of the most interesting out of equilibrium physics, the most interesting dynamical phase transitions, are situations where the entanglement has one property or another. Yep. During some dynamical regime. And so entanglement is really a sort of a convergent topic of interest in many different places in condensed matter theory.
Yeah, it's definitely something that like more broadly just sort of overlap in sort of like how different fields sort of influence each other, even with how that's something I really want to touch on eventually in a video, because it's like you'd be surprised how much sort of conversations, how many conversations are going on between people that are looking at, magnetic materials versus people who are looking at black hole physics.
Yeah,
right.
Absolutely. I mean, the interesting connection there, and I think, have you done a video on Scramble?
No, that's definitely in the books. That'll be. There's so much I want to talk about, but I'm only doing one video per week, which is like I couldn't possibly do more. But of course I want to talk about everything.
Yeah, absolutely. I mean, scrambling I think is one of those very cool topics. So scrambling, maybe for folks who are interested, is this question about actually very much related. At the beginning of your video on Anderson localization, you have this great graphic, and it shows how you've got a sort of very particular set of initial conditions. No two subsystems look identical. They're all sort of randomly distributed. You allow the system to evolve in time, it equilibrates, and the consequence of equilibration is that it looks the same everywhere. And so you've lost information about the initial conditions. And the question of scrambling is really about that. The question of scrambling is really a question of, I make some change to my system. Maybe I kick the system in some way, or I kick a degree of freedom in the system in some way. How long does it take before I can't even tell that happened? How long does it take for that information to sort of be assimilated into the system?
Yep.
And there's a concept of maximum scrambling time. So Lieb and Robinson have this famous proof in the field, the famous bound. And the bound is a bound on how quickly information can propagate. Now, people watching might be familiar, if they're into popular science, they'll know that Einstein, there are these famous experiments by Michelson and Morley where they showed that the speed of light looks the same no matter whether you're moving with it or against it or orthogonal to it. And a consequence of these experiments was that Einstein posited that the speed of light is fixed. You can't go past the speed of light. And indeed, when we look at the universe around us, that seems to be true. You go to CERN, you can put energy in, and you can get particles to 99.999% the speed of light or some ridiculous high fraction like that. And no matter how much energy you put in, you can't get them over the speed of light. Well, Lieb and Robinson, totally independently of that, and I think this was done maybe in the 60s or 70s, so this is a bit of an older result by now. It's a classic result. Showed that the speed at which information can propagate in a quantum system, independent of relativity, just on the grounds of quantum physics, is fixed. There's a sort of speed limit based on the nature of the interactions in that system for how quickly information can propagate. And so systems which I don't know, there are a few different definitions that sort of float around in this area of physics, but the idea is that a system which sort of saturates this bound, systems that respond to a change in information and scramble that information away at the quickest possible rate, they're called maximum scramblers. And the theory is that a black hole, the surface of a black hole, is a maximum scrambler. If anything falls into a black hole, it's gone. That information is never going to be, even if that information is leaked back out. There are many theories about how the information that falls into a black hole might dissipate back out into the universe. This is called the black hole information paradox, right? So the black hole information paradox just says, well, quantum mechanics tells me that the evolution of a quantum system preserves information. So I can wind the system forward, I can wind the system backwards. Information is always preserved. Incidentally, that's true in classical mechanics as well. If you look at the classical equations of motion, you run them forward in time, backward in time. They work just as well in one direction as in the other. If I know the equations of motion for a system, I can always unwind it in principle. And the problem with black holes is this idea that if you fall into a black hole, you can't get out, right? I mean, light can't escape a black hole. Nothing can go faster than light. Therefore, nothing can escape a black hole. So when information falls into the black hole, what happens? Like, where does that information go? Is this a problem? And this is called the black hole information paradox. And so one of the solutions to this that I think is quite appealing is this idea that black holes have a very complicated structure in their surface. The surface of the black hole is very complicated, and it's complicated in a way that when information falls into it, later on, one day, that information will be re-emitted again in the form of Hawking radiation. So the black hole is one of the reasons Stephen Hawking is so famous. He established this idea that black holes do evaporate. They actually do emit something back into the universe. That something is Hawking radiation. And this Hawking radiation carries with it the sort of scrambled information that fell into the black hole. And so this is a sort of solution to the black hole information paradox, or a proposed solution to the black hole information paradox. And so these black holes, these maximum scramblers, are therefore connected to these condensed matter systems where we might ask the same kind of question. I might imagine a system of magnetic moments. I disturb one of them, and I ask the question, how long does it take before I can't tell that disturbance happened? And the physics of a magnetic system that is a maximum scrambler is in this sort of very deep way connected to the physics that's happening on the surface of the black hole. It's sort of like a kind of a wild connection. You almost couldn't think of two more different physical systems than a black hole and a fridge magnet.
Yeah.
And yet, fridge magnets are not. Fridge magnets, incidentally, I don't think are maximum scramblers. But magnetic systems that have physics sort of similar in some sense to a fridge magnet could be a maximum scrambler.
Yeah, if you're watching this and you've ever heard of the out of time ordered correlator, it's been a huge topic for researchers in black hole physics and then also condensed matter physicists. And that's basically what the OTOC, or the out of time ordered correlator, is attempting to measure.
Yeah, there are many sort of approaches to this problem, and it engages some of the top minds currently working in the field. So I think that this is something that if you're a young undergraduate student, or you're just starting to get into graduate school, it's the kind of thing that you might want to think about learning about. It's a very cool area of physics if you want to sort of be doing something that sits at the nexus of condensed matter and cosmology. It's kind of a cool middle ground that you can explore, which I certainly didn't know about when I was an undergrad. So
it's a strange middle ground. I definitely didn't think that would somehow exist. But I guess it makes sense, right? Like, I mean, physics concepts are always maybe not always, but usually it's there's some applicability. Physics concepts have some substance that are sort of more general than the thing that you're applying them to.
I think that's very true, and I think that what you can see looking at condensed matter, we might have talked about this in some of the previous streams, but what you can see looking at the way that condensed matter physics is done today is the very clear influence of particle physics.
Yep.
So in particle physics, you want to consider situations, you've got your standard theory of quantum mechanics, and the problem with quantum mechanics, there are a couple of problems with quantum mechanics. So one of the problems is that space and time are not treated in the same way, and in relativity they are. And so you need to find a way of generalizing quantum mechanics to a theory that puts space and time on equal footing. So in particular, in quantum mechanics, time, as we sort of mentioned before, there's no operator associated with time. Time is just a parameter.
Yep.
And position, space, is an operator. And so the solution to this problem is you sort of demote space. You demote space to the role of being also just a parameter. Mm-hmm. The other shift you have to make is to find equations of motion for your system that put space and time on equal footing. And the first attempt at this was this so-called Klein-Gordon equation, which actually had been discovered by Schrodinger. He was trying to work on the same problem, and he discarded this solution because there's a paradox, a well-known paradox called the Klein paradox, which is that you get these sort of negative amplitude solutions when you sort of scatter things off of a boundary, off of a fixed wall. And so people didn't understand how to interpret that in the context of the wave function. And what's really happening here is that, everyone knows this famous E equals mc squared, right? So if I have E equals mc squared, that means that energy can be converted into mass. And that means if I have two particles, say 2 electrons, and I get them really, really close together, they want to repel, right? So there's a huge amount of potential energy that gets stored up when they come really close to one another. And if that potential energy is so big that it is equal to the mass of another electron, say, or an electron-positron pair, then you have this potential for particles to be created in that process. Or if I have, say, an electron and a positron, they fall into each other, they can annihilate and produce light. And in those two contexts, our sort of standard story of quantum mechanics just doesn't work. Quantum mechanics doesn't handle that situation. And so quantum field theory is the technology that got invented to deal with these types of problems. Mm-hmm. And in the structure of quantum field theory, what we sort of understand is that the universe is filled with a field called the electron field. And the excitations of this field are the electrons. And it's coupled to a field that fills the universe called, the photon field. That's the field of light. And these two fields are coupled together. So when two electrons come into each other, we understand them as excitations of this underlying field, and they can scatter and create new excitations or annihilate each other, all the sort of physics that we'd be interested in studying. So in condensed matter physics, we care about what happens in a material, right? What does that have to do with condensed matter physics? Condensed matter physics is happening at low temperature. It's happening at low energy. In a condensed matter experiment, I'm not reaching anything like sort of relativistic energy scale. So why is this technology so useful to us? Why do we work in the language of quantum field theory? Well, if you take, for example, a simple conductor, okay, so imagine a conductor, and imagine your starting description for the conductor is that you just have electrons, and the electrons are sitting in the lattice. They don't see each other. They don't talk to each other. Okay, so that's a simple theory of the electron. But now you say to yourself, well, okay, but electrons do see each other. They repel each other. Mm-hmm. They're both negatively charged, so they repel each other through the Coulomb repulsion. I want to add the Coulomb repulsion into my theory. What happens? It turns out that what happens is that the states from before, the states that were sort of the free particle, free electron states, get transformed into states that look just like the free electron states, but with a different mass and a different charge. Mm. So the excitations that you get, this is called, for the aficionados, this is called Fermi liquid theory. So a Fermi gas is the first scenario. A Fermi gas is just electrons. They don't see each other. They don't talk to each other. Just, n electrons in a box. And Fermi liquid theory is what happens when I turn on Landau Fermi liquid theory. What happens when I turn on the interactions between the electrons? What does the physics look like? And so, okay, so then what is this excitation in the Fermi liquid theory? Well, the excitation is a kind of emergent excitation. It's a kind of excitation that is coming from the complicated screening effects of these electrons, which are repulsing against each other, but then also sort of blockading the repulsion from one another, because the electrons are sort of everywhere in space. And you can cast this theory in this language of what we call a quasi-particle. So the quasi-particles in the Fermi liquid theory, they look like particles, they behave like electrons, but they aren't electrons. In fact, they are superpositions of 1 electron states, 2 electron states, 3 electron states, all the way up to n electron states. All of those states are actually contributing to the state that is the quasi-particle state. And so what we find is that we can make these sort of effective field theory descriptions of materials. We can look at a material and we can say, okay, well, what's the symmetry of the material? What's the dimensionality of the material? And we can concoct a theory of how the excitations in that material behave, but in this language of particle physics, where an excitation gets created, an excitation gets destroyed. That's not because the actual electrons in the material are getting created or destroyed. It's because an electron which is getting bumped up and sort of screened and interacting with all the other electrons, that's happening, and then that electron is sort of losing that energy, dissipating that energy, and we're coming back down to a kind of Fermi C scenario. So the Fermi C, where all the electrons are undisturbed, is playing the role of the kind of vacuum field, that kind of electron field that pervades the universe. And the quasi-particle excitations are kind of like these little analogy electrons that are hopping up out of this vacuum and behaving like weakly interacting particles, just like we would see in the context of high energy physics. And so this has been an extremely fruitful language. I think it really got developed in earnest in the kind of starting in the 1960s. These ideas really began to take hold. And now if you look at the literature on how phase transitions are understood, it's all really in terms of these theoretical models that cast condensed matter systems as systems of weakly interacting quasi-particles or weakly interacting collective excitations. In this sense, incidentally, it's kind of like there's a universe inside every material. It's kind of like as if every single material contains within it its own little universe with its own little laws of physics and particles that could never exist anywhere else. When we started this discussion today, we talked about the fractional quantum Hall effect and how in that theory, the electron looks like as if it is fractionalized into pieces. In the ordinary universe, the universe we live in, the 3+1 dimensional universe we live in, the electron is believed to be a fundamental particle. It has no inner structure. But inside of a material, the complexities of the way that the material is interacting can give rise to this emergent physics, these fractionalized excitations. So, I think that, this is assimilating this language into condensed matter has been sort of one of the major achievements of the 20th century and continues to be a fruitful paradigm for studying condensed matter systems.
Yeah, absolutely. That's I mean, you really said everything that was
Sorry, that's
fine.
It's fine. Just so excited there talking about quasi-particles.
I love it. I love it.
If we, it's amazing to see. I think this is something that people really need to appreciate about also. I sort of take the view that this is true of, and I think most scientists. This is something that is not controversial. Most scientists, I think, would agree with this. Good science comes from collaboration.
Absolutely.
Good science comes from when you have the group of people doing project A talking to the group of people doing project B, and those folks are sharing ideas, sharing techniques, sharing perspectives. That's where you get real progress.
Absolutely. Yeah, I couldn't. I definitely couldn't agree more. So we're approaching the end of the stream here. We got 6 minutes. Not a very lively chat this time, but that's of course fine. A lot of people end up finding this video by the over the course of the next few weeks. A lot of people find the video. Do you perhaps we could tackle a few Reddit questions? How would you feel about that?
Yeah, sure. Let's do that.
All right. So one interesting question that a user had called "Take off your mask." I don't think that that's related to COVID. His account seems to be older than COVID. One of the questions that they asked, or not him, they, I don't know the gender of this person, of course. If this breaks statistical mechanics, then what happens for the law of increasing entropy? What's your take on that?
Sure. So I suppose that this person is asking whether or not the second law of thermodynamics is still true. Is that
that seems to be the case? Yeah.
That's a very interesting question. I guess I would claim that the second law of thermodynamics states, okay, so to be clear, right, it states that globally the entropy of a system either increases or stays the same. And I don't think that anything about Anderson localization contradicts that fact.
Yep.
And so that's the important thing to remember. In fact, the entropy of a system, in a quantum mechanical context, entropy is conserved by the unitary dynamics of quantum mechanics. When we spoke earlier about this idea of information being conserved, that's really what we mean, right? Is that unitary evolution keeps the entropy constant.
Yes.
And so there's nothing about Anderson localization that breaks the second law of thermodynamics. Indeed, I think in this context, when we say that Anderson localization breaks StatMech, I think what we really mean is that Anderson localization, and I didn't make the title of the video, but what I infer the title of the video, and John, maybe you can tell me if I'm inferring correctly, is that Anderson localization doesn't give rise to statistical equilibrium ensembles that we would normally expect.
That's what I mean by the title. If that wasn't, you're absolutely right. It's that no matter how long I wait, I will not reach something that looks like equilibrium that agrees with an ensemble from statistical mechanics, even if you take the most, in the free fermion case, you can construct something called a generalized Gibbs ensemble. And if I was to construct a generalized Gibbs ensemble with the conserved quantities, which scale sort of linearly with the size of the system, your local subsystems would not agree with those expectation values anyways. You just don't really build up the entropy required. But you do build up entropy. The dynamical processes do build up entropy. So processes in these systems do build up entropy. You always have increasing entropy. It's just that it just doesn't build up a lot because you have these area laws versus like with the ground states that James was talking about.
Definitely.
So another user had the question about conservation of information, which I think you've covered covered quite thoroughly. Another user had the question of not really being sure about why Anderson localization sort of illustrates a counterexample to statistical mechanics, as it's actually just a single particle problem.
Sure. So I think so. There's a generalization of Anderson localization to the many-body case where you include interactions between. It's called many-body localization.
Yep. So
you include interactions between the particles, and you see whether or not the localization behavior is robust or not. And I believe the answer to that is yes. That
it seems to be yes in the 1D case, but I think that it's also fair to draw sort of come back here a little bit and say, if I can write down a Hamiltonian for you, and then I say I'm going to keep adding in more and more particles, I'm going to start increasing my degrees of freedom. The fact that free fermions, like in this model, in the Aubrey-Andrew model or the Anderson insulator model, the fact that these can then be diagonalized so straightforwardly to a non-interacting model doesn't necessarily mean that it's not a valid question to ask whether or not statistical mechanics can emerge when I have lots and lots of fermions or electrons hopping on these lattices and doing all that stuff. And in fact, when you don't have disorder, there's lots of people, including myself, who have asked this question in research articles. When you don't have disorder, something that looks like statistical mechanics does absolutely emerge. You have generalized Gibbs ensembles, and it turns out that in special cases you can even get canonical ensembles that well describe your subsystems, etc. So it is a single particle problem in the sense that I can diagonalize the Hamiltonian and express it in a completely single particle problem. But when these electrons are sitting on this lattice and they're equilibrating and all this stuff, they are building up entanglement. It's just admittedly a simpler example than the so-called interacting case, but it's certainly worthy of studying and sort of a nice test case to see what happens, because we have complete analytical control in it, right?
Yeah, I think there's something here which I think is sort of a bit of a value judgment somehow. When we say something is the counterexample to stat mech, I mean, what do we really mean by that?
Yeah,
I think
right.
there's some room here for people to have different definitions about what would constitute a sort of valid,
Yep.
like sort of counterpoint. I want to say something like, if you think about traditional thermodynamics problems, say the ideal gas, right? Part of the idealization of the ideal gas is that the particles in the ideal gas aren't interacting with each other.
Yep.
Okay, so is that a one-body problem?
Kind of.
Kind of, yeah, right? It's kind of a one-body problem. It's still a problem that is sort of accessible to statistical mechanics. I can still talk about the stat mech of a one-body case. Fair to say, I mean, maybe that's not, in the spirit of a fully interacting theory of stat mech, just because the Anderson localization is a one-body problem, a non-interacting problem, a free problem, doesn't mean that it doesn't have bearing on the emergence of stat mech. And I think it's just true, it's just uncontroversial that this is a system which doesn't exhibit the behavior you'd expect the system to exhibit at finite temperature. You expect finite temperature things to equilibrate, usually. And so this is an example of a system that doesn't do that. And indeed, even when you include interactions, there seems to be some pretty good evidence that this system doesn't give rise to the sort of standard statistical ensembles that you would expect. So, from that point of view, I think fair to say that it's definitely an exceptional case. And I mean that's why it's interesting, right? Like if it wasn't different from what we would have expected, then no one would be talking about Anderson localization today. The whole point is that it's different. That's why we're interested.
Yeah, it's different. It's surprising. For me, it's really interesting. I guess it is at the end of the day sort of sort of a judgment call of where do you see these questions actually being asked and where are they interesting? And certainly for me, I don't know. It just seems like if you have analytical control, it's a really interesting question to ask for these single particle problems.
I actually noticed on that Reddit comment where that question was asked, the person who asked the question also asked or also raised the question about whether or not the Andre Aubry model is exhibiting Anderson localization.
So this is okay.
Periodic and not random.
Yeah, I love this question.
Yeah. I think that's an interesting question to ask. I'm not an expert on the Aubry model, but I think that it's worth noting, right, that when you make random numbers on a computer, you do it with a periodic function, and it's a periodic function that just doesn't repeat on the scale that you're sampling from it, and that's how you make randomness. So, the idea that quasi-periodicity, for those who are not aware, right, if you have a lattice and you have a periodic potential would be a potential that repeats on some sort of scale over the lattice, maybe so every second site or every site or every third site, the potential repeats itself, and so that's periodic on some length scale that is sort of commensurate with the lattice. But a non-commensurate periodicity is a situation where I have a wave, maybe a cosine potential. But in the argument of the cosine potential, I put an irrational number, or I put a rational number that doesn't divide the size of my lattice, so that on the scale of my lattice, every single site is experiencing something kind of non-periodic. There's no pattern, in other words, that I can pick out on the scale of my lattice. I'm going to kind of go ahead and say, as far as I can tell, that seems effectively random to me from the point of view of the physics of the lattice. I don't know. maybe there's some proof that that's not true. Maybe there's some evidence that that's not true. But as far as I know, that is really the same thing.
There's this really fascinating article that I had up that I have up just in case this sort of came up, and it's called "Localization by Biochromatic Potentials versus Anderson Localization" by Matthias Albert and Patricio. I'm gonna butcher this. Leboeuf. It looks like a French name. Very, very fascinating sort of conversation that they have is that you can take these models or attempt to take these models to their semi-classical limit and then look at sort of their classical orbits. And it turns out that so if you take when you have the Anderson insulator and all of the potentials are generated randomly, you can sort of do this convolution trick to sort of approximate this behavior. I don't really understand this step of the paper, so perhaps at a later point I could explain this better. Basically, you get it when you take this to the semi-classical limit. You get that it has an extended phase for zero disorder, and then the semi-classical limit, you get. I believe what happens is that you get the transition doesn't happen until where it would happen for the Aubrey-Andre model. So the Anderson insulator has classical orbits that are extended, even when you have a finite disorder, I think is what happens.
I see.
And so that means that on the quantum level, before you take the semi-classical limit, there's a localized portion of this model that is purely quantum mechanical. It's quantum mechanical in nature, and it doesn't have an analog in the semi-classical limit. But when you do the same thing with the Aubrey-Andre model, it's extended where it's extended quantum mechanically and semi-classically, and it's the same with where it's localized. So when I tested the localized portion of the model in the video, both the semi-classical orbits would have been localized as well, and they would have been localized for the Anderson insulator as well. But then if I instead, yeah. So anyways, so there's this special region for the Anderson insulator that is purely quantum mechanical, and the localization is quantum mechanical, sort of in nature. So the authors of this paper claim that this is a clear distinction between these two models.
Interesting.
So that's definitely really interesting. So good on good on them for pointing out the.
A good distinction. Definitely not one that I was aware of before. Certainly.
But
yeah, it's very interesting.
But then I guess that it's still like the localization is localization. Once you get the eigenstates that are Anderson, let's I'm going to call Anderson localization for the sake of this conversation single particle, free model localization. Then the properties are basically the same between the two models. When the two models are both localized, after that certain critical point that these authors point out, it's the same. So what you were seeing there in those dynamics was Anderson localization.
I see.
So it's definitely an important point, and I don't think, a lot of authors still call the Aubrey-Andre Anderson localized sort of regardless. I don't think the community really has it set in stone, or it's not widely sort of perhaps appreciated or not in such a way that what Anderson localized means it has like some very strict definition, if that makes sense.
Interesting.
But it was definitely a cool thing for someone to point out in the comments. I definitely appreciate having people who know enough about the topic to bring stuff up like that.
Yeah, certainly. I mean, that's a very I definitely appreciate having a chance to understand that subtlety for sure. Yeah.
Perhaps that'd be an interesting future video. So someone actually asked in the Reddit thread for an MBL video. I don't have data sort of lying around for myself. I think that'd be a fun thing to potentially collaborate on.
Yeah, that'd be very cool. It'd be cool to talk about MBL. I think that's a very interesting topic at the moment. So, yeah, certainly.
But yeah, so it was fun. Let's wrap up the stream here. It was really fun having you again on the stream. I had a good time.
Yeah, my pleasure as always. Yeah.
So for the two viewers, thanks for hanging out with us. We'll talk to you another time. All right. Thanks so much again, dude.